Hi, in this video, I want to introduce you to the unit of measuring planar angles, okay? And it's called radians. And also, hopefully, by the end of this video, I'll also try to prove the formula that the length of an arc of between 2 points on the circumference of a circle equals to the radius of that circle times the central angle subtended by those 2 points on the circumference of a circle at the center of the circle. And if you have no clue what any of that meant, you're in luck, because I'll be explaining that, how to prove it, how to visualize it, how to use that formula, what that formula actually means, and everything related to that. However, before we actually try to dwell more into that, we have to first understand the concept of radians, okay? And let me just write that down. The word radians. Radians, as I've already said, it's a unit that we use. It's a unit that we use to measure angles. Measure angles. And it's actually the SI unit. SI is once in the long form, it's actually translated one from French to English. It's the International System Unit. It's a convention, the metric convention that nearly all countries use. So the radians is the sort of the convention unit to measure angles. However, when I talk about angles and measuring them, there's another unit, another term that comes in our mind, and that's degrees. So let me use that in red. Degrees. And degrees, that's the unit that we have sort of grown up learning while we were advancing our skills in geometry and other fields of maths. We were using degrees primarily, and radians usually comes when we start talking about trigonometry and advanced fields of maths, such as calculus and other fields. So why are we using radians, and why is radians the convention or the SI unit? I'll explain that in this video. So let me first just try to tell you and just define on board what 1 degree actually means. You know, when we say degrees, it's, you know, we know what to do with it. We know how to use degrees in trying to measuring angles in various shapes. But when I say what 1 degree is, by the way, this is the symbol of a degree, and I bet you already know this. I'm just gonna put that in. The symbol of a degree. So if this is the magnitude of a degree, x degrees, I don't know what x is, it could be anything, x degrees, and then we just put that symbol, that notation, and this would mean that we're referring to x degrees, okay? And so coming back to the question, what does 1 degree actually mean? So, what does 1 degree mean? Well, we know that there are 360 degrees in a circle, right? So we can just define it simply, very simply and briefly, that 1 degree is 1/360th of a complete revolution in a circle, or sort of the complete revolution around the circumference, around the perimeter of a circle, which is the circumference in a circle. That's sort of the definition. And we can use this definition of degrees in other shapes. So 1/360th of a complete revolution, okay? So if I have a circle now, and this is the center A, let's say, point A. This is an R circle, but I think it's fine. So once we join it to any point, it doesn't matter where it actually lies on the circumference. So let's match it over there. Okay. And once we now start to rotate this arm, sort of this radius, this is the radius. Once we start to rotate this radius from the initial arm to whatever and reach it to whichever point we want to reach it. So if we rotate it like this, and this is our final arm, this angle that has been formed by the two radii, this is also radius, okay, by the two radii is measured in some degrees, right? And usually for knowing like an unknown variable, we usually refer to it as x or y or whatever letter. And for an unknown degree that we don't know, it's a variable, we don't know what it is, we refer to theta, okay? We refer an unknown degree as theta. We represent it by theta. That's more correct way of saying it. Represented by theta, and theta is the Greek. It's a Greek alphabet, and so this we don't know what it is. If I tell you it's 30 degrees, then we know that theta actually equals to 30 degrees. So this is 30 degrees. This is theta degrees. Okay. So what is 1 degree? So 1 degree is 1/360th of a complete revolution. So now let me erase this and let me draw a bigger circle. Okay, let me draw a bigger circle. Actually, I'm going to draw here. And this is the point A, okay, again. If I, again, just join it with any point on the circumference and make a complete, over there I made an acute angle, right? So over here, if I make a complete revolution around the circumference, reach back, the angle that is formed at the center, so this angle that's formed here would be 360 degrees. So that's what the second half of this definition means. Okay, so 1/360th of this the degree of this angle measure would equal to 1 degree, and that's sort of the definition, the universal definition of a degree. So it would be 1/360th. So it will be something like this. So if we divide this angle 360 degrees, this angle 360 degrees into 360 parts, one part would measure 1 degree. Okay, and now that seems a bit logical, because we actually start to understand, we start talking about degrees from 360 degrees, then we move on to 1 degree. Okay, so it seems more logical. However, if we went the other way, it wouldn't. And by the way, if you're just wondering and if you're just curious why we measured 360 degrees, it's a random number. Actually, it has something to do with the history behind using degrees, and how the Babylonians actually, they had measures of angles back then, and they used 360 degrees as one full measure around a circle, because once they were trying to observe stars and observe other planets and other sort of cosmic elements, they figured out that it takes 360 turns or 360 degrees to go around another planet or just another celestial object. Okay, so this is why we choose 360 degrees. It's an arbitrary term. We can use 100 degrees and we can use 200 degrees. So it really doesn't matter. So, but 360 degrees is the convention. So coming back to radians, because that's the focus of this video. And yeah, so if you really didn't understand the actual meaning behind why we actually chose 360 degrees, I encourage you to actually search it up and try to learn it, because I myself don't know much about it, but it has something to do with observing the stars and their trajectories around other celestial objects. Okay, so coming back to radians now. Radians, so we understand what degrees are. Okay, we're very clear with degrees. So let me just erase this now and let me talk about radians. So let's talk about radians. And radians, I don't want to put the definition straight away because that'll be hard to understand if you don't even know what it means in a circle, because we know what degree now means. We have visualized the concept of a degree. So I'll do the same thing with radians, okay? So I'll just draw this big circle, okay? And irregular. So this, let's say, is the center. It could be any point, I don't know, M. Center M, okay? So this is a circle with center M, we know that. Now, we know that if I choose any point among the infinite points on the circumference of a circle and just join it, so it'll be better to understand the concept of radians if I just do it at the same line that joins it. So I just chose this point, okay, and this point, let's say, is P, okay? So we know that the line that joins points M and P, that line is the radius, okay? And we know what a radius of a circle is, okay? And so now we can use, and by the way, there are two ways to visualize the concept of radian. So I'm talking about the first way of trying to understand what a radian means. We can use this radius MP. So I'll just use this radius MP like over here, okay? And I'll choose this length, and I will make it erect so that it is perpendicular, and it's the same length MP, okay? So what I'm doing is I'm now just extending from point P to a line that to a line segment to a point M, extending it to point M. So now I know that these two line segments are the same, they have the equal length, and that length is the radius of a circle, okay? And let me just put that as just putting it perpendicular to that point, or to that line, this horizontal line, okay? So these are perpendicular and they're both the radii. Now if you look carefully at this line MP, if I try to right now try to curve it such that this line coincidentally intersects all the points on the circle, or if I just try to bend this line, this perpendicular line, such that it just, fits just the right amount on the circumference of a circle, okay? So let's say, okay, it won't be that much. So if I bend it, it'll be something like this, okay? And this is the same value, okay? So this is R, and because I haven't increased or decreased the value of R, it's constant, I have just manipulated the shape of that length R, okay? So now this point, let's say this point M, because M has been bent and has been forced to coincide on the circumference of the circle, so that point is again M, okay? So these 2 points MP now form an arc. That arc is on the circumference of the circle, and those 2 points, once connected to the center, this is already connected to the center. Once point M is connected to a circle, or actually I should not use M because it's already here, but you get the idea, right? We're just rotating it 90 degrees over here. So it will be better to use another variable, but you get the idea, so I'm just gonna put it there. Okay, so now this value was R, so even this would be R, and so is this. This is R, length R. So the angle that's formed from the point M and P, in this case, the angle that has been formed by points M and by points P, points M and by points P, it would be some angle theta in the center, and that angle theta equals to 1 radian, okay? And this is very important to understand. This is by the way one way to visualize what one radian actually means. This is 1 radian. So we understand 1 radian is the angle from the center. Okay, it's an angle formed from an arc that was on the circumference which had subtended that 1 radian, and the length of that arc was r units, r meaning equal to the length of the radius. Okay, so this is, by the way, one way to trying to understand concept of radian. And by the way, the other way, these two methods that I'm going to explain, this one I've already explained, the other method that I'm going to explain, they're one or the other way, they're one or the other the same thing. Okay, so let me just quickly try to understand what I've just done over here, so I can just now define 1 radian based on what I have understood and seen. So 1 radian in this case, 1 radian is that, yeah, 1 radian, it's the angle formed at the center, the angle formed at the center of the circle, which has been subtended by 2 arcs, or which has been formed by 2 points, by 2 endpoints of an arc, which is actually a better way to put it if you are getting confused with the word subtended. Okay. At the center of a circle, which has been formed by an arc on the circumference, or the endpoints of the arc, 2 distinct unique endpoints of the arc, okay, by an arc on the circumference, which has the value, or which has its length equal to the radius of the circle. So which has the value, or which is equal to, actually, make it more simple, which is equal to the radius of the circle. So the length of the arc is not some random unknown unit. We know the value of the length of the arc, okay? And what that length corresponds to the center is 1 radian, okay? So this definition is not going to change the same. I'll just try to change the representation of the concept of radian on the diagram. Okay, so I'm also going to just use the same diagram as well, the same circle. And this time, let me make it more regular. Okay, this is again, I chose last time point M. Okay, so point M. Now, once again, if I were to just join this point M to any point, let's say again, P, on the, and by the way, this is the second method, okay, the second method of trying to understand what the radians actually mean. If I were to now try to if I were to join these 2 points, M and P, essentially what can happen is that this is my radius. So now if I move on this side, so now these points M and P, so this is of length R. If I now try to start forming an angle, because we know an angle has 2 arms, the initial arm, so if this is an angle, this is the initial arm, this is the final arm, because it's sort of the final arm is the initial arm which has been rotated on one vertex to some point, to some other point, okay, and so the angle that was formed between those 2 points, between those 2 arms is the angle, right, measure of the angle. And so the final arm is essentially just the initial arm, but rotated to another point above or below the initial arm, the actual position. Okay, so if this is my initial arm, let's say, okay, now I'm rotating it, you know, I'm constantly rotating it. And remember, note, the initial arm, or this arm, my final arm over here, is corresponding to some point on the circumference, right? That's a point there. Decrease the value, or decrease how much I rotated. That's a point over there on the circumference. That's a point. That's a point. Okay, so I'm just rotating this radius to some point. Okay, I'm rotating it, and then I am rotating it to the extent to which the point that corresponds to the point that's joining, or the point that corresponding to my final arm on the center, on the circumference of the circle, that point to point P would be equal to the value of R, or the radius of the circle. So I'm just sort of increasing and rotating my initial arm to an extent such that the arc that's being corresponded at the circumference would equal to R. Okay, so that was one way, trying to bend the rotated radius that we have done, and this is another way, trying to understand that, and both of them are the same thing. You know, it's the same definition now. Okay, so once we join it, could be one radian again, right? 1 radian. So the same definition. So that's the sort of representing, understanding what a radian actually means, and we have understood it now, and we've also defined it clearly here. Okay, so as I've told you before, the symbol for degrees is the superscript, this symbol. So the symbol for radians, there's actually 2 or 3. There are many symbols for using radians, but the most common symbol is just the word RAD and dot. So that actually means radian in a full form. Okay, and there's also superscript, like we use for the degrees, for the full circle, the small circle. For the radians, it's a C, a superscript C. So x, the magnitude of radians of the value of the angle, is x radians with the superscript C. Okay, so we can just use both of those units, or both of those symbols. Okay, and now we have understood radians and we have understood degrees. So now you might be thinking, okay, so both of them measure the same thing, right? Both of them are measuring an angle in a shape or in a circle. So wouldn't there be any relation between the two? Because we know that any 2 units that are measuring the same thing, right? A meter is measuring the length of anything. A foot is measuring the length of anything. We have a relation between a meter and a foot, right? The same thing applies here. We have a relation between the 2 units of measuring angles. And so the relation between radians and degrees goes as this. So the relation between radians and degrees is that one degree equals to around 57, or actually it's 57.2958. Okay, so that is rounded to around 57.3. So it's around 57.3 radians. Okay, 1 degree is equal to 57.3 prox radians. Okay, and 1 radian would equal to then the reciprocal of that value, which would be 1 over 157.2958, which equals to 0.01743 degrees. Okay, and if you again want to round this, it can be around 0.02. Okay, 0.02 degrees, or because that actually more, let me just maybe 17 degrees. So 1 degree is around 57.3 radians, and 1 radian is around 0.017 degrees. Okay, so yeah, I understand that, but why did I get, and why is this why are these numbers in the relation? Why is there 57.2958, or why is there 0.01743 as the relation, right? So to do that, we have to come back to the circle and try to understand where both of these angles are measuring the same distance or the same unit with the same magnitude, okay? And that's very important to understand, because that's only when we get relations. So if I draw this circle, let me just erase that as well. So let me make the circle occupy this part of the whiteboard. So yeah, let's see, circle. Okay, and you have a point, I don't know, A. Now, what I said was the two units, radians and degrees, we can only find a relation between the two once we find out where the two units are measuring the same thing with the same magnitude. And so we know that one entire revolution in a circle is one entire revolution of a circle corresponds to the one entire circumference, right? One entire revolution of the circle from the center, okay, from the center A, on the circumference, that degree, okay, that measure, or not degree, that measure of the angle corresponds on the circumference to the entire circumference, right? To the entire circumference. So it is not equal, you can't equal length and degree, angle, it corresponds, okay? So that's corresponding to, okay? And one entire revolution in degrees, we know it is 360 degrees. So 360 degrees corresponds to one circumference, or corresponds to 2 pi r, which is one circumference, okay? So now we know how many degrees corresponds to the circumference, how many radians corresponds to the circumference of the circle, okay? And now we've understood, we know the definition of radian. It's the angle formed by the arc that subtends that equals to the value of the radius of the circle, and it subtends at the center of the circle. That's the measure of 1 radian. So now let's say, okay, let me do the same thing again. Let's say this arc over here between the points B and between the point C equals to 1 radian. So let me just join this to the center, and yeah, you know now this is 1 radian. You also know that the circumference of this circle C would equal to 2 times pi times r. So we can think of it as r is being added 2 pi times. Okay, it's very crucial to understand this part. So r can be added, you know, if we add r 2 times, we know it's 2r. If I add r 3 times, I get 3r. So if I add r 2 pi times, or 2 pi is approximately 3.14, right? And 2 times 3.14 would be equal to around 6.28. So if I add r, the radius, 6.28 times, so r plus r plus r plus r, 1, 2, 3, 4, plus r plus 0.28 of an r. plus 0.28 of an r. Okay, this would equal to the value of the circumference. Now note, the value of r on the circumference corresponds to 1 radian at the center. So let me draw it again. So this one arc of measure r corresponds to 1 radian at the center. So let's say, let me extend this to another point such that this point, so BC, and this point D over here, once joined to the center, this arc subtends another radian. Okay, so the arc, the big arc over here, when you look at the big picture, CD, this whole thing corresponds to 2 radians, right? 2 radians. So now, how many times would I have to make these make these arcs of equal lengths r radius such that it covers the entire circle? It comes back to this. I would need 2 pi of these arcs, right? Because I know that one arc has the value r. So 2 pi of these, or 6.28 approximate of these arcs around the circle would give me the entire circumference. So I know that now. So I'm just going to write that. So this is degrees, and over here I'm going to talk about radians, okay? So 1 entire revolution corresponds, around the center A corresponds to C, which is 2 pi r, okay? So now I know that 2 pi, so 2 pi r. So I know that now 2 pi r radians, 2 pi r, this is 2 pi r radians with the superscript C over here, okay? Because I know that I would need 2 pi of these arcs, each of length radius, to complete 1 entire revolution. And what does that correspond at the center? 1 arc corresponds 1 radian. So 2 pi arcs would correspond or subtend 2 pi radians at the center. And each arc has the value or the length of this equal to the radius of that circle, right? So now I know this. I know that 2 pi radians, not 2 pi r radians, 2 pi radians at the center corresponds to the circumference, which is 2 pi r. Now this is 2 pi r, this is 2 pi r. This is how we figure out a relation or deduce a relation once we know that 2 different distinct units that are measuring the same thing, which is here an angle, when these 2 form the same angle, once these 2 come and join at the same, or once we're dealing with the same magnitude, then we can find a relation. So we know the magnitude over here is 1 full rotation, 1 full revolution, 1 full revolution. Okay, so now I know that. So now I know 2 pi radians, or let me just write it over here, radians, like this, or we can also use the superscript C, equals to 360 degrees. So what would 1 radian equal to? 1 radian would equal to 360 degrees upon 2 pi, because if you multiply the left hand side and the right hand side by 1 over 2 pi, you get 360 upon 2 pi. So let's see, let's simplify this. So 180. So 1 radian equals to 180 degrees over pi. Okay, so 1 radian, 180 degrees. This is the logic behind why this works, okay? And what is 180 degrees? So if I simplify pi, so let pi over here be 3.14. So 180 over 3.14 would give me approximately, and if I do that on a calculator as well, it gives me approximately 57.2958. 57.2958. So that's where we got the value in the relation that I had written earlier. 180 over pi. And now let's see. This is my main relation over here. What's 1 degree? So I know what's 1 radian in terms of I know what's 1 radian in terms of degrees. What's 1 degree in terms of radians? Well, then I've just multiplied this by 1 over 360 times 1 over 360. Let me just use green because I don't think you can see. Yeah, now. So I would get 2 pi over 360. So this 2 cancels with 180. So 1 degree would equal to pi over 180 radians. Okay, and so now this, once I do it on a calculator, it comes to around, it comes to around 0.01743. Okay, around 0.01743, which is the same value that I had written down earlier. Okay, so it's very important to know the logic behind the formulas as it is to know what the formula is actually talking about. Okay, like why we have 57 point, or why we have 180 over pi. That's the logic over here. And now I know that. So for the sake of making simple calculations, I'll just use refer to 1 degree as pi over 180, not 0.01743, because that would complicate my calculations. And 1 radian I would refer, and this is by the way radian, or just rad dot. So 1 radian would be referred as 180 upon pi upon pi degrees. Okay, so better to use pi because it eases your calculations and your solutions. Okay, so now let me just solve a very simple question over here. Let's see. I have, let's say, 30 degrees. So in this circle, from the point A, center, I make an arc, I make an angle of 30 degrees. So what would 30 degrees be in radians? So it's good to just now note and remember that relation. So 30 degrees. So I know 1 degree is pi over 180 radians. So 30 degrees would be 30 times pi over 180. You have pi over 180 30 times, right? Radians. And so now let's simplify. 3 times 6 gives 18. So it would be pi over 6 radians. Okay? If I just give you any other number, let's say, I don't know, 27. Yeah, 27. So 27 degrees would equal to pi over 180 times 27 radians, right? Let's see. So 9 goes 3 times in 27, 2 times in 18. So it would be pi. It would be 3 pi over 20. And that's, I think, how much you can simplify. That's the most you can simplify. So that's, that's 27 degrees. So 27 degrees is 3 pi over 20 radians, or rad, or the superscript. Okay? So now let's talk about that formula, that relation. And if you're just wondering why we use radians in the first place, why can't we just have one unit? Well, as we dwell more and explore more in the higher fields and the more higher advanced level fields of mathematics, such as advanced trigonometry, calculus, geometry, we'll see that, especially calculus and trigonometry, we'll see that if you have some basic understanding of trigonometry, if we're trying to find the trigonometric function of any angle in terms of degrees, if we use radians, it eases the number of steps we use to write in a solution, okay? And also in calculus, that's where they come in handy. Okay, so now we know that in higher levels of maths, radians are beneficial to degrees, but both are the same thing, right? Both have advantages, both seem complex, but both have their own advantages. Okay, so yeah, now let's try to expand the concept and utilize it more in arcs and in relationships with the central angle. Okay, so now let me formulate. So that formula that I was talking about, the length of an arc equals to the central angle times the radius. So let me draw the circle again. Okay, this is the circle, center again A. So that formula, it states, it's a relationship essentially between two units. It's a relationship between the length of an arc on the circumference, right? The arc's on the circumference. So I don't know, let's say this is arc BC. Arc BC. That length would be equal to the radius AC, the radius AC, or the radius AB. Okay, the radius R times the central angle that this arc subtends at the center. So this is called the central angle, the angle subtended at the center, okay? And this is in theta. Like I said, we don't know the value of theta. So the length of arc L equals to R times theta. This is the relation. But why does this relation actually occur? How can we prove it? And to prove this relation, I'm not going to use any hardcore math. I'm not going to use any math. We're just going to imagine why it occurs, why it happens the way it happens, right? So we just have to now visualize this formula in our minds. Visualize it with this circle. Okay, so the formula is asking us to form a relationship between the length, the radius, and the central angle. Okay, now the length of this arc, say L, well, it subtends an central angle theta, and the radius of that circle is R. So this is theta. Okay, and let me make this in font. And by the way, just a very important note, in this formula, the value theta can only be used in radians, okay? It can be used in radians. If we're going to use in degrees, we have to then divide it or convert it back to degrees. But the formula, it's the angle has to be in terms of radians, okay? So theta has to be in terms of radians. Okay, so now, let's see. This is L. This arc of length L, if I were to ask you a question, how many times does R fit in L? Okay, how many times? So how many times does R? So let's say this L, this is the length L, okay? This is the length L. Okay, this is this curved piece over here. And if I were to now flatten it over this, make it straight, a full straight line. It could be any length, right? It could be L, which could be like all the way over here. It could be all the way over here, this whole thing. But let's say over here, let's say it's this much. This length L, if I were to ask you a question, how many times does R, the length R, fit in L? So if this was L, once straighten out, and if this is the value of R, Well, let me see. If this is r, if this is r, okay, and let me see, this is like 1/4 of r. So r fits 3 times perfectly in L and 1/4 in L. So it'll fit 3/1/4, right? 3/1/4 of r equal to L. So the number of times r fits in L would equal to, so L would be basically divided by r into, let's say, x number of times, okay? So L, we divide it into r x number of times, okay? Now, this value r, it's somewhat similar to what I was telling about the radius being curved to the circumference, or being curved to the perimeter of the circle, such that it forms 1 radian. So now think about it, okay? We know this is, by the way, just the frequency of r in L, which is x times. So now if this is L between these 2 points, so let me add these points A, B, and C, okay? B and C. This value r corresponds to, once this value r is on the circumference, that value of r, I don't know where it is, let me say it's here, okay? That corresponds to 1 radian at the center. So 1 length r corresponds to 1 radian at the center of the angle, at the center of the circle. So let's say if I have 3 r's, so let me right now just deal with 3 r's, okay? This is point C. Each r corresponds to 1 radian at the center. So 3 r's would correspond to 3 radians at the center, right? So r fits in L 3 times. Each time it fits, it corresponds to it corresponds to 3 radians. So 3 radians. Okay, and now this we can easily now deduce the formula, because the number of times r fits in L is equal to the number of radians at the center of the circle, at the central angle. Okay, so this x is nothing but r theta in terms of radians. So L over r equals to theta, the central angle, okay? And so L would equal to r times theta. We have just proved our concept, our formula from this concept. And so what we just did, it was nothing complicated. We didn't have to use any other theorem, any other rule. We just had to imagine how many times does r fit in this L, and because we already now know r corresponds to 1 radian, x number of r's in L that fit would correspond to x number of radians, which is theta, our unknown variable. So this is how we prove it. So let me now just solve one question. And this is very helpful. This relation is very helpful. So let's say if let's say the length of an arc is, I don't know, 30 centimeters, okay, and the circumference of the circle is around let's say 6.2, or no, the length of the arc, let's say the length of the arc can't be more than the circumference. So let's say the length of the arc is 30 centimeters and circumference 62.8 centimeters approx. And let's take pi as 3.14 in this question. So we have been given the length L arc, 30 centimeters, circumference 62.8 centimeters, and we have to find the central angle theta. Okay, we know the length, we know now the relation. We can think of it in our mind. It's the number of times r fits in L, which is basically the central angle. We know L, we know r, we don't know r, but we can find out from the circumference. So we know C equals to 2 pi r, 62.8 equals to, let's see, 6.28 r equals to 10 centimeters. So length of the arc 30 centimeters. What's r? 10 centimeters times theta. Theta equals to 3 radians. Theta equals to 3 radians. Another question. This time I'll give you radians. This time I'll give you the central angle, okay? Let's see. Central angle is around, let's see, I don't know, 45 degrees, okay? 45 degrees. Length of the arc is, again, 30 centimeters. What is the radius of this circle, okay? It's very simple. Here, theta has been given in degrees, not radians, so we have to put them in radians first. So what is 45 degrees in radians? Well, we know the relation now between radians and degrees. 45 degrees times pi over 180 degrees. 45 goes, I think, yeah, 45 goes 4 times, so that's just pi by 4 radians. Okay, now, length of the arc, 30 centimeters, pi by 4 radians. So length divided by the central angle gives r. 30 divided by pi divided by 4. The 4 goes up, which is 120 by pi, which is the value of the radius of the circle. Okay, so we can check it back, we can verify it. So 120 by pi radius centimeters times the central angle. What's the central angle? 45 degrees. Pi by 4 would give me the length, right? So this would give me the length, because we know this is r, this is theta, the central angle in radians. This pi would cancel, this would equal to 30. So 30, 30. And so this relation is very helpful, helps us in a lot of questions. And the good thing is we've understood we have understood two concepts: radians, how to convert what it is to degrees and what it all is, and we've understood this formula from a very simple circle with just an arc and a radius and a central angle. So that's the beauty of mathematics. We can derive more and more statements, more and more formulas, more and more functions from very simple basic building blocks. Okay, very simple concepts. We can derive more. And hopefully in the next videos, I'll be deriving more on this, building more on radians, trying to extend your knowledge of trigonometry to an even farther frontier. And that's it for this video. Thank you.